Welcome everybody. We're going to try to start on time so we can keep on schedule here. My name is Rob Quick. I'm going to be hopefully a relatively silent moderator, but we'll be here to help things out. I did want to welcome you to the current session B. This is integrating functionality across domains and tools. We have 3 presentations, 1 live presentation to start things off, and then 2 pre-recorded presentations, but I see that all of the people who are representing them are here. So what we'll do is go for approximately 12 minutes for the presentations and then do 3 minutes of questions individual to each presenter. And then at the end, we'll have 15 minutes of a group discussion to see how to pull everything together and try to get some common discussion going around the 3 presentations. So let's see. Please do use the notes that are available, the shared notes that are in Kiko chat. Please, if you do have questions that pop up during the middle of a presentation, put them in chat and I will either ask you to unmute at the end of the chat or present those questions to the presenters. And I think we'll go into the first presentation. It is our net.science, cyber infrastructure for sustained innovation in network science and engineering. And that'll be done by Chris. And Chris, if you want to share your screen, you can take things away.
Okay, thanks, Rob. Let's see, let me move this over and I'll go into presentation mode. Okay, can you see the screen okay?
I can.
Great, okay, thanks. So this project is net.science. It's a cyber infrastructure for network science and engineering. The team members are down the left and right columns. My name is Chris Coleman. It shows up at the bottom. The 4 folks you see across the bottom are kind of leading this effort. Dustin is the lead architect, Madhav is the PI, and Ravi and I do a lot with the computational codes and some of the infrastructure, okay? So these are the topics we'll cover, some background and motivation, and then a quick overview. We'll take a look at some aspects of the cyber infrastructure fairly briefly, the software infrastructure, computational codes, the networks and data, and then we'll go into education and outreach and summarize. So right now, the cyber infrastructure can be accessed at net.science as shown at the top of the page, and all this cyber infrastructure is right now is 4 static web pages. And so what we'll be talking about is our work over this first year in getting the cyber infrastructure up and running, and talk just a little bit about how we're going forward. So we haven't quite completed the first year of a 5-year project, okay? So our motivation for doing this CI, first of all, networks themselves, they're ubiquitous. People interact with networks almost every day, if not every day, of some sort. There's wide academic interest in networks. A number of companies have their businesses predicated on interactions among people. And some of the examples are shown at the bottom of this slide. So the motivation for the cyber infrastructure, as we just saw in the previous slide, the wide use of networks is one, but the second aspect is a couple of observations, and that is many operations on networks are common across application domains. For example, computing connected components, the number of connected components on a graph, it can be done without regard for what the domain is, and then it's the analyst who interprets the results for the specific domain of interest. And so that's our general approach for this project, is that we want to build a general purpose cyber infrastructure for network science. And so this is from a user standpoint, we're focused on operations and computations, and then data, which are primarily networks. And we can handle domain specific types of codes. That's not a problem, but we want to make this as broadly appealing as possible. And so what we're trying to do is then say, okay, the analyst who runs the computation, it's their job to apply the meaning to the results that come out of the system. And so as far as we're aware, there's no general purpose network focused cyber infrastructure, but in fact, there are a lot of CIs, as people know. Coincides has some 40 gateways or more, but none of them are devoted specifically to general purpose network science. And similarly for SGCI, there's about 600 gateways, and well over a dozen of them analyze networks for particular contexts. But again, we are trying to focus on a general purpose CI. Okay, and so the URL is shown at the top again. And for us, our cyber infrastructure is a combination of the web app, computational codes, data, primarily network and network related data, and then the software infrastructure. And so the system we're building is going to be open access and mostly open source. So the only time we wouldn't have it open source is if someone contributes a code, for example, and they say they don't want it released, then of course we're going to honor that. We talked about general purpose network science. And so the idea is to analyze and visualize primarily network data or network related data. What we're hoping to achieve is that producers and consumers are both motivated to come here because of its use and the ability to put new codes and data into the system that can hopefully attract users. So even contributors, for example, might come up with novel algorithms that they implement, and we hope that they would see value of contributing to this system, because we'll keep track of how often the system is used, so that they might use that, for example, for subsequent NSF proposals. And so clearly then we're also hoping to foster team science or provide a platform for team science. So here are the cyber infrastructure core components. At the top, we have the two green boxes. The left box is the net.science web app. I spoke a little bit about a couple of slides back. The other green box is for external applications, for example, RStudio or Python notebooks, things of this nature. If we could drill down or go down one level, we have the net.science API. This is the entry point into the computational backend, where we have core services, for example, file service, job management system, and user service for user authentication, as well as the computational codes. And on the left, we have supporting services such as the digital library, or digital librarian, which we'll look at in the next slide. And then down at the bottom, we have computational resources. Okay, and so this is just one view into the system to look at this digital librarian. So at the bottom of this graphic, again, we have these blue boxes representing different services. And on the top, we have the net.science API. And on the left, where the purpose of this slide is for the digital librarian, the blue box on the left, that it has access to all the digital objects in all of these different services, along with the metadata for each digital object. So it can access this data, manage the data, represent it in different ways to expose, in this case, search facilities for the user. So for example, they might want to search on what kind of codes exist for computing strongly and weakly connected components, or they might be interested in doing analyses on graphs of particular sizes with other types of properties in the graphs, so that this digital librarian then supports this type of searching. Okay, so these high-level features that we're working on right now are login and user management of managing user accounts. The web app, we just spoke about searching before of different types of digital objects. It will also have user interface screens for all the different computational codes, which will generate automatically. And then this notion of team science with viewing, plotting, sharing the data. As far as uploading into the system, in the shorter term, we're looking at networks and network type data. We'll say something about network type data in a few slides, in that people who contribute these types of artifacts, they'll have the ability to set the permissions on these objects. So for example, viewing the objects or whether they can download them, and other types of settings. Then of course, there's a job service to run operations on networks, where right now we're looking at our back-end hardware being either high performance computing clusters and GPUs. So multi-core nodes and GPUs are hardware on the back end. And then we have the API, which the web app uses, and third-party code. So for example, we mentioned RStudio before, and Python notebooks would be examples of third-party codes that would directly access the API for more compute intensive operations rather than always going through the web app. So this is just to give a glimpse of the job service and how these computational codes exist within the system. So on the right, we have singularity containers, one for every code. We have the executable code in its environment. And then in the middle, we have the execution targets, excuse me, where the codes can be run. And on the left-hand side, we have input and output file specification, so that if someone submits a job, they specify inputs, for example. These input files that they specify will be compared against specification, so that if the files aren't valid for the particular use, users will be notified upstream as far as possible, rather than having the job be submitted to a Slurm queue, for example, and then only find out something is wrong once the job starts, after it possibly has been setting in the queue for a while. Okay, so the early codes, the computational codes that perform operations on networks are shown here on the left-hand side. But rather than go through those, basically what we're trying to do is hit two categories of codes. And these are, again, just the early codes that we're dealing with. The one category is the high user base codes, okay? So people who do a network analysis, a lot of them, they're going to expect codes like Snap and the Network X libraries to be available because they have huge user bases. But on the right-hand side, we're also interested in putting novel codes in right away. And some examples of this are reliability, polynomials, SAT solvers. And so SAT solvers, you can download these codes and run them on your desktop. But as far as we know, or as far as we're aware, that there's no cyber infrastructure that has SAT solvers in them. And these are useful because a lot of different problems can be reduced to SAT problems that then can be solved and mapped back to the original problem. So these are codes that we're dealing with right now and inserting into the system. Another type of analysis on networks is structural analysis. So we're working with the Snap library and the Network X library. These codes need a little more attention because every code in the system has to run in its own address space as a standalone application, which means, for example, with Snap and 130 methods, we need a main method to go with each one of the library methods. And so we constructed a pipeline to automatically parse out comments and the method signatures, develop main methods in the pipeline so that we can perform these operations, get the codes that we need, and to put them into the system. And so we are working with Network X also. We have about 270 of those methods that we've generated thus far. And these are all going into the system. Another example of a computational code is contagion dynamics on networks. So, you know, an SIR model or SEIR model with the COVID epidemic, you know, is a prime example these days, but also social contagions like the spread of fads and things of this nature. So we start out, so we're using open source tools to the extent possible, right? We don't want to reinvent anything. So this EON code stands for Epidemics on Networks. We've modified the code to do other types of models that we're interested in and that are very common, for example, in the data mining literature. And so we've put together a small system here where the simulation model consists of the EON code that we modified. Then we have a data analysis code that takes the simulation output and puts it in forms for plotting. And then we have a plotting module where the users can generate publication quality plots. And a couple of examples are shown down here in the lower left.
Chris, just to interrupt you here, you have about 1 minute left.
Okay, great. Thank you. So the network categories, we have graph generators that are that come from the structural analysis codes. We're mining graph that exists on different web pages. And we're also generating data that then in the right box can be used to generate networks based on definitions of what those networks are, okay? So basically what we've talked about so far, and this is the last slide, is the education and outreach, okay? And so in 2020, we've worked on getting the cyber infrastructure, the basic functionality in, and we're going to release it to the public in 2021. We're also going to have network science courses taught with net.science CI, and the folks here are going to use that. And we have outreach operations going on where we're going to have workshops to demonstrate the CI, and we're also going to have a high school program in the summer of 2021. So I'll just leave it at that. Is that okay, Rob?
Great. Yep. Thank you, Chris.
Thank you.
So we have 3 minutes for questions. If I didn't see anything come through the chat, but if anyone has a question they'd like to ask Chris, please speak up now. If not, I have a question that I'm curious about, but I'll let everybody else get a chance first.
Can I get in a question?
Sure, absolutely.
Yeah, hi, everyone. I'm Arjun. Chris, thanks so much. The question is it possible to integrate tools that we have developed into net.science?
Yes, we would have to talk to you about the specifics, but we specifically do want to integrate other codes. You noticed on one of the slides I mentioned as far as uploading networks and data. Mm-hmm. We do want to have users have the capability to upload their own codes. But as you can imagine, that is a much more difficult problem than uploading a data set, right? Because there's issues of how does it run, what kind of resources does it need, depending on what kind of inputs, parameters that users specify. And then there's always issues about security.
Yep.
So, but yes, we are going in that direction, but not like within the next year or so. So yes, we could talk after the meeting.
Sounds great. I'll get in touch. Thank you.
Okay, thanks.
Okay, thank you, Arjun. It also looks like Mike Zentner has a question. Mike, you want to ask that, or would you like me to?
Sure, I can ask. Basically, I was curious about whether you have to use novel database architectures for the underlying data here to support large-scale computations, and if so, what are some of those database management systems you use?
Okay, so the database we use MongoDB for a lot of the architecture, but I think you're asking about how to store large size graphs, for example, in the system. And so what we are doing is we are using the approach that the Stanford people use with Snap. And basically they have a data type that's called a table. And basically the networks are stored as tables. So there's, let's say, a node file, and it can have, for each node, it can have any number of properties of floats, ints, strings, and same way with the edges that where you have, let's say, 2 nodes that form an edge, and then any number of properties on each edge. And so they have a number of different types of operations that come with their system. So, for example, doing different types of join operations. So if you have a multi-graph, you can separate the different layers of the graph in different files and then compile them or build them together, start doing union operations. And so that system scales right now to, I believe, very low, like 1 billion nodes, okay? And then more edges. And so we specifically looked around and we talked to the Stanford people about their capability and decided to go with that first. Hypergraphs will present their a slightly different issue when we get to that point. Does that answer your question at all?
Sure, and we need to move on, Chris. So Mike, if you have follow-ups, please feel free to contact Chris. And Chris, I actually have a question about how the digital library manages digital objects, but we don't have time for that now. So we'll either get back into that at the end of the session in the discussion, or maybe I can run into you sometime offline.